Okay, good afternoon, everyone. We continue with I2C or I2C serial port. Okay, I2C stands for integrated I2C stands for integrated circuit bus. Okay, it was developed by Philips and now they call NXP Semiconductors.
Sir.
Yeah.
Sorry, can you speak louder?
So I did something.
Because the sound is very soft at my side. I'm not sure if I'm the only one have this.
Everyone has problem with my voice.
No. It's just like quite soft actually because I opened the maximum volume already.
Let me see. Is there something I can do with that? Maybe something to do with WebEx itself. Let me see. Okay, give me some time.
Is my voice loud?
Yeah.
Your voice is loud.
Maybe
are you using a headset with a microphone?
Yeah.
Oh, okay. Because I'm using the same thing as well. So
yeah,
maybe some configuration on your side.
I
Because
so.
he's right, because your audio is kind of soft, but I can increase my volume on my side to maximum lah.
Yeah lah. So right now I think in this WebEx there is a setting to increase the volume, but when you want to use it, you don't know where is it. Manage? No, not this one. Any idea? It is a setting to.
All right. So if you look, if you stop sharing for a while, okay, and then you can see down there are buttons like mute, start video, share, right? Click on the mute. There's a small arrow there,
okay,
and then there's settings.
Yep,
okay, and then under the settings there is a microphone input level and input volume. You can adjust. Did you find it? Did you find it?
Yeah.
All right.
But my voice now is almost full in the input level meter.
Okay. All right. Maybe the input volume you can increase higher.
Yeah, this is the input volume. This is maximum, and my voice here in the meter is already very high. So
I see.
think I will use. Let me see. I try to use the microphone array. Okay, now.
Can't hear you.
Testing. Is it any better or same?
It's a bit louder, but the quality is lesser, in my opinion.
Yeah, because I'm using microphone that is on the laptop.
Yeah. Let's ask the other participants. Is it acceptable?
I think should be okay.
The new one. Okay, this current one, is it okay?
Yeah.
Let's use this one lah. Input level automatically adjust volume. Okay, I put automatically adjust volume. Is it better? Testing. Same.
I think the same.
Okay lah. What to do? My voice is also already weak. Everybody knows that. So what to do? Can't change the nature. Okay, so
soft spoken, they say.
Yeah. What to do? Okay, so I2C, yeah. So okay, I2C or I2C is shorthand for integrated circuit. It was developed by Philips for use in TV actually, originally, and was a patented protocol but expired. The patent expired, and the characteristic of I2C, the main characteristics is a synchronous serial. Okay, that means it's totally different than UART or RS-232. And it's a multi-master architecture, which makes it different than some other kinds like like USB. Okay, USB, for example, there's only one master and multi-slave lah. I2C is multi-master, and it uses open collector bus driver. Okay, which is plus and minus lah. Okay, so when you have an open collector, that means when you want to connect components to the bus, you must have a pull-up resistor, but you can add and remove devices from the bus quite easily because it's open collector. So it's not like if you have 3 there, you cannot move, you cannot add, make it 4 or make it 2 components in the bus. Open collector is easier to attach and detach peripherals, but because of the open collector and the pull-up resistor, this also means that the data rate is slow. Okay, so it is slow but robust. That means in error terms, there's not so much error, so quite reliable, simple and low cost. Okay, so originally it's intended for operation on a single PCB, even until today lah. So most of the I2C that we see is a single PCB, and using I2C you can reduce board space because there's only 2 pins or 3 pins that you're going to need for one connection, so you can reduce the number of total pins on the overall system. And because they are also, because this is simply for simple board and for simple system, you must locate the components closely. You cannot put a peripheral that is using I2C far from the intended recipient of the data. Okay, so many devices are available with I2C or I2C. Okay, microcontrollers definitely, and then we have EEPROM, LCD drivers, A2D, and so on. And you can find this all over the place lah. Because originally the intention was in EVs. Okay, so I2C has 3 speeds: slow, fast, and high speed. So high speed means 3.4 megabit, which is still slow lah. If you compare to the current USB, the high speed is slow, and then it's limited to about 10 feet. But almost nobody I see use I2C for 10 feet lah, because remember that the original intention is for use on the same PCB. So PCB is small, not going to be, you're never going to reach 10 feet. Okay, so this is the basic configuration of I2C bus. Normally you have one master at least. You must have one master. You can have more than one, okay, but normally only one, and then many slaves. And outside chips, you need to have 2 pull-up resistors, one for each of the 2 wires there, and then of course you need a ground. Okay, so 2 lines, data line and the clock line, and they are all multi-tap, so all connect to the same pin on the same node. And because of the open collector, again, we need to have a pull-up resistor, and anytime you have pull-up resistor, you're going to slow down everything. But it's the price to pay lah for the ease of connection. And because it is open collector and using pull-up resistor, so you can mix. I think it is safe to mix 3 volts and 5 volts in the same chip, in the same system. And it has a bus arbitration, so if 2 devices wants to transmit at the same time, it has some knowledge, or it has the ability to still cater for that lah. So it's not totally the transmission will not totally fail, but because of the arbitration, sooner or later the device that is trying to send data will have the chance. Okay, this is how the data is transferred. Okay, so the clock, if you see, just look at the clock. Okay, first refer to the clock at the bottom. So unlike a normal clock on the system, which is always running, here you only see the clock when data is being transferred. And the clock line is high when you're going to send data, and then it could be low for some time when you want to do clock stretching to cater for slow devices. So idle is high, and then it will go low only when you have data coming in. Okay, so for when you want to transfer data, it has same idea like UART. Okay, you want to send data, the data line becomes low. Otherwise, it's by default is high, but when it becomes low, it's a signal that the transmitter wants to send data. So if you look at a certain place here, before clock number one, we have the clock high, and then suddenly it become low. Okay, so when the clock is low and the data is 0, that means we are at the start bit. We are trying to send data, and then afterwards we have 9 clock pulses, and with the 9 clock pulses we have 7 or 8 address bits. So we have here A6 going down to A0. That is the address bit. So you send the address, and then we have the signal whether to read or write, and then we have the acknowledge. Okay. So before you transmit anything, the clock must go from high to low, and then 9 cycles, and then at the same time you send the address, and then you send the data. Okay. So step number 1, master starts communication with start. Okay, and that was how start is signaled by the combination of clock and data. And the master sends the address byte, and the address can be 7-bit. And some certain devices now we have 10-bit address. Okay, so the default is still 7. And then after the slave address, it is followed by the read-write bit. So can be slave receive or slave transmit. And then the slave confirms the section with the acknowledge bit. So here, the green box, the green vertical bar, or the ACK column, that is given by the slave. Okay, so the rest, the read pulses here is by the master, but the act there is by the slave. So there is a signal from the slave saying that it is ready to communicate with the master. And then the master continues with another set of 9 clock pulses to transfer the data. So clock, after the word clock stretching here, which is optional, okay, in case the slave needs to slow down the system or the transmission. So the master give another 9 clock pulses, and at that time the transfer is done. So that D block, the black or gray area on the top right of your diagram here, it can be coming from the slave or going to the slave. And after all that, the clock goes high again. That means we're not going to transfer any more data, and then the data is idle again. So for every byte of data you transfer, you need 18 clock cycles or 18 clock pulses like that.
So
yeah,
can I ask a very basic questions? What is the difference between the master and slave?
Okay, master is the one controlling the transfer. So normally the master is the microcontroller lah. Here we see I2C microcontroller master. So if you have a device that input data, for example, you have analog to digital converter, so data will be coming in lah. So then the slave will send data to master. But if it's a output device like the DAC, then the master sends to the slave. So the master control the whole operation, but the data can be coming or going. Okay, did I answer the question?
Yes, thank you.
Yeah. So the red one, so the red colored pulses here, it comes from the master. So the master gives the address, and then the master gives the clock to do the transfer. And the address, most of the time is determined by the manufacturer. When you buy any component, when you buy any peripheral, normally they give you the address. So you have to use the address. Okay, I need to give a quick example because I just I have an example later. Okay, so just leave it lah. Okay, so the red one comes from the master. The green one here, the egg, comes from the slave, and then the black one can be from the master or from the slave, depending on the data direction. Okay, and then it's okay for the master or the slave to send data, and there will not be a problem electrically because you are using open collector. So that's safe lah. It's no problem. It's not like a AND gate or typical gate lah. AND gate or gate that TTL. Okay, you cannot have two or more devices driving the same wire at the same time. Open collector, no problem. Okay, here, there's a legend here. Master red, green is slave response, and black one can be either the master or the slave. Okay, so depending on the direction of the communication, the master or slave now send any number of data byte. Okay, and then each byte is confirmed by the egg bit. Okay, so here it is possible for the address appear only once, but the data can have multiple set. You don't have to give separate address for every data. Then the transmission can be aborted using the NAC bit or not acknowledged, and there is abortion lah. I want to abort the transmission, but for proper transmission, the master stop it by using the stop condition, where it is the rising edge on the SDA with the SCL high. So there is a stop condition here. It's a rising edge here on the SDA signal, and during that time, the clock is high. The stop here is SCL high and falling edge. Okay, so you can have master sending data and master reading data, and then the data bytes can be n data bytes. But for each data byte, you have for each data byte you have one acknowledgement. So first you send the address, and then send data. After you finish, then you stop. Or if you already data, send data, receive data, and then stop. So the address here can be for the whole block. So it depends on the device that you are communicating with. So each node has a unique 7-bit address, and the device address is fixed at the factory. And some part of it can be programmable, depends on the device itself. So we have 7-bit for address, and the 8-bit is for read or write. And then the addresses are assigned by Philips. Now because the patent is over, probably they still do it, but they cannot charge for the use, but they still manage the address assignment. And then there are some addresses with special functions. Okay, so this is example of the address. Okay, so there's a specific address, and also there's an address which is encoded in a device, and there's some part that can be changed. This one, nothing new. Okay, we can skip. Okay, so now on I2C on STM. This is the block diagram of what's inside the I2C block in STM. So we have SDA, SCL, then first stage in front is a noise filter, and then of course the shift register, because this is serial data transmission. You have to convert serial to parallel, parallel to serial. And there's a control logic there and so on. Okay, so on the STM32, it is multi-master, so the same interface can act as master or slave. So the STM32 can become a slave device. And then the speed is only standard and fast. Okay. Let's cheat a little bit, go back. What other speeds are allowed? Slow, fast, and high speed. Okay, so no high speed. The 3.4 megabit is not supported by STM32. Okay, and then we have two interrupt vectors for each of these blocks. One for successful data transfer, and the other one is for error condition. Okay, so I have one example here. TMP102 simple temperature sensor. Okay, so let's look at how the chip looks like. Okay, I have it. Okay, so this is how the chip looks like. So this is the chip itself, and if you want to interface with your STM32, you need a breakout box because the chip is so small. You need to have a breakout box to have the connection. So here you can see you need only SDA and SCL, which is of course the same signal as I2C process standard. And then the address is 0x48 by default. And voltage is 1.4 to 3.6. And then you can see here the default for Arduino is 3.3. Normal, this is Arduino. This is just to show the voltage tolerance is quite large from 1.4 to 3.6 because it is open collector. If you use normal TTL, you never can never see this kind of voltage tolerance. Okay, so it's a simple temperature sensor. Address is 48 hex, and then the output is 12 bits. So the first byte is temperature in Celsius, and the second byte contains the Celsius divided by 16. Okay, so how does it look like? Where is my gem water? Okay, this one. Okay, so there will be two haha. I think my pen is out of battery. Like this, using the mouse. Okay, it's like this. Okay, we have 2 bytes. So byte number 1 contains the Celsius. Okay, and then byte number 2 is Celsius divided by 16. So let's say your temperature is 1.5 Celsius. Example only, yeah. So I will have 0, 1 here. And then 0.5 in binary will be 1, 0, 0, 0. And then 0, 0 here. So I will have, in binary, I will get 1.1 binary. But the data itself is 12 bits. So 8 bit from the top and 4 bits from the bottom. So if you want to make it a 12-bit number, so first maybe you read it from the top one. Okay, this is byte number 1. This is byte number 2. So this one you don't want. Okay. So if you have to shift 4 times. So then this one goes here, goes here, goes here. Then you have 4 zeros here. But the number here is still not exact. Basically, the number here is Celsius. If you consider 8-bit here, okay, so this is 8-bit here. And the Celsius is only up to from bit number 4 to bit number 11, but the last 4 bit here is divided Celsius divided by 16. So the whole magnitude here is actually Celsius divided by 16. So whatever you see here, you have to divide by 16. Or if you want, if you just want the Celsius without the fraction, you just take the top one. So this is the Celsius only. On this part, this is the Celsius only. If you want more accuracy, then you take the top 4 bit from the second byte. Okay, so first byte temperature is Celsius. Upper bit of second byte is upper 4 bit of second byte is Celsius divided by 16. If you don't want the fraction, just take the first byte to bother with the second byte. So this one looks complicated. We need to send the address first, okay, 48 hex, send it to the device, and then we write to register address 0, and then this will tell the chip to send data. So later we have 48 hex and then read. Okay, see this bit here. By the way, we have bit the yellow bit here. Okay, there's a yellow bit here and then the green here. Okay, so that is a write signal and this is a read signal. So when you want to read the data, send 48 and then 1 there. After 48, you send bit 1 there. Tell the device you want to read the data. And then afterward, the XXX here is the data from the device. So the data here will be 2 bytes. So 1 byte acknowledge, 1 byte acknowledge. So the total frame or total characters transmitted is 5. So first one send 0, and then first two characters or first 2 bytes send 0, and then followed by 3 bytes of data transfer. First the address and then the data itself. Okay, so this is how we connect. If you have STM32, there's SCL and SDA on the board there. Okay, then there's a ground, so connect the ground, and then if you have the breakout board, so just look up 3 or 4. It's like 4 here. So you need a ground and a power supply, right? So this is 3V3. The red wire is 3V3, 3.3 volts, and then the black is ground. So connect 4 wires, and you see the code. Okay, so you see the code, not this one. Okay, so when you want to use I2C, there's not many functions, not that many. You have to know which one. So if you want to transmit or receive, there are 4 HAL functions. The first one is HAL I2C master transmit, and then we have HAL I2C master receive. So we use these 2 if the if the microcontroller is acting as a master. Yes, the master want to transmit or receive. Then we have HAL I2C slave transmit or HAL I2C slave receive. So this is when the STM is acting as a slave. Then these functions are blocking. That means it will wait until the transfer is completed before going to the instruction after the function call. And then the second group here is device memory read or write. So this is useful when the I2C device is a memory type. Okay, so not all in this example just now, this is temperature sensor. So you only read one piece of data. It's a Scala. Just one piece of data, and then that's it. If you want another piece, you go read it again. But if it's a memory type, you don't want to give too many. Want to reduce the number of transactions. So what you do is give the address once, and then you read a block of address. So the function call is different. So that's called memory write and memory read. This is also blocking, where it will hang lah. So the moment you call this function, it will hang, or it will wait until the loops are completed before you can proceed with the next instruction. And then we have interrupt mode, which is non-blocking, and DMA mode, which is non-blocking. Okay, so as we know, interrupt and DMA, they can be used to make the processor do two things at once. So for example, transmit and then just let the device take care of it, and then when you're finished, tell me. So what's the function call? It has to be different. So here we have interrupt mode and DMA, different function calls. Well, of course, more work lah. Before you can call this, you have to set up the vectors and the callbacks. Okay. So what is a callback? Callback is a function that is in computer science is called executable code that is passed as an argument to other code. So you call a function, but when you're calling that function, you give the address of function as the argument. I don't see it here, but it's still called a callback lah. So when you're using interrupt or DMA, you must use a callback with a special name. So you must use master TXC PLT callback. Okay, this one special format, special name. You must have a function with this name in your code. And of course, inside there, whatever you do, you have to define, but the name has to be standard, has to be exactly like this. So this one, the first one, is called or is executed after all data is sent by the I2C master transmit IT or master transmit DMA. Okay. Go back here. See this, when you transmit, you either transmit using interrupt mode or DMA mode. And when you transmit, and the transmit is finished, so this function will be executed. You don't have to run it yourself. You just prepare the function, and when the DMA or interrupt routine is finished, this will be executed. So you can put something here like message or set a global variable telling the main program that the transmission is done. When receiving, also same idea, but of course this is for receive, and the name is slightly different lah. Before it's on top here, master TX, here is master RX. Different by only one character. Okay, so this is an example of reading data from I2C device that the MP chip just now and send it to UART. So all this junk on top here generated probably by STM cube and so on, but some you have to add yourself. For example, the TMP102 address is something that you have to write, but here you can see that the 0x48 has to be shifted to the left. Okay, so somehow you cannot just use 48, even though the 48 is the address. because it has to do something with the data bus arrangement in the STM32 lah. So just follow this, shift it by 1. Then here in the code, you can see you have to prepare a buffer because you want to convert the temperature that you read into a string, and then you have the value that you read. And after that, after the variable declaration, we have the HAL init as usual, system clock config as usual, GPIO init, and then we have UART user init and I2C init. Okay, so we have 5 functions from line 21 to 25 that are probably generated by STM32. You have to do them yourself. But this is our user code. Okay, so for this code, I forgot to put the number on the left, so very harder to refer to the line. So in this code, we transmit we transmit because we want to tell the device that we want to read it, and then you have to check whether you get the code HAL OK or not. Okay, so if you don't get HAL OK code, then there's an error connecting to the device, so you basically give up lah. You cannot even talk to it the first time. Remember that to talk to this chip, you have to write once and then you read. So you have to write 0 first. You have to write to register 0. This is like a dummy or to tell the device that you want to read it. So write it once. If that one doesn't give you OK, error lah, because you cannot even send data to it. And then if this is OK, you try to read 2 bytes. So here you can see here RET. This is RET means the value that you use this to store the data. Wait, I think I left. Okay, this here. Okay, HAL status type def RET. Okay, so RET here is the place to store the error code. Okay, so you just execute master receive, and here in the parameter you have add I2C1. This is the handle, and then we have the address here, TAM102 address. Okay, then buff. This is the address where you want to store the data that you receive from the device, and then 2. So 2 here is the number of bytes that you want to read from the device, and then we have the maximum delay. Okay, so this number is quite random lah. Yeah, you can put any number. If you put, actually this number is unbelievably large. It can be days. So if not okay, you put an error and then send that. Later we'll see that the buff here is a message that you're going to send to the UART. Okay, so if no error, okay, if you somehow successfully go through this code without any errors, you will go to this code here, val equal integer 16, shift left by 4, and then all with buff 1 shift by 4 to the right. So that is this thing lah. Okay. So the first one, actually you have this one, you go to the left 4 bit, and then this one go to the right 4 bit, something like that lah. So we have this funny, scary shift and OR combine the bytes. But if you just want to have the Celsius and not worry about the fraction, of course, the step is simpler. Now, you want to convert that to 2's complement. So to convert to 2's complement, you have to check this bit. Okay. If this bit is 1, you have to make this 1, 1, 1, 1. You want to make the 12-bit value into a 16-bit 2's complement. So if val is greater than 7FF, that means actually it's another way to say that this is 1 here. Then you OR with F000. Convert that to 2's complement. Then that value, you multiply by 0.625. This magic 0.065, this is actually same as divide by 16. Remember that this value here is, the whole thing here is actually Celsius divided by 16. So the actual value is 1 times 0.065, or just, you can also write it as 1 plus 16. And we have some tricks here because we want to send that as ASCII. So we have to separate again the ASCII and the integer and the fraction. So multiply that by 100 and then divide that by 100 again. Okay? Multiply and then divide again, so that you have two parts. You have two parts. The first part is the temp underscore c divided by 100 is the integer part. Temp underscore c modulo 100 is the fraction part. So when you combine, you will get string here. Can you see on the bottom right here? It's like the terminal output. Okay, if you send this to the PC, and on your PC you run UART, you run PuTTY and the UART, so you can see the temperature values. So this one can be simplified if you decide, oh, I don't want fraction. I can save maybe 2 or 3 lines. Probably there's another way to make this simpler. Okay, so that is example. So for how to use I2C, so quite okay lah. Just if you want to try, you have to know the address, and that's it. And just make sure you check for errors. Okay, so advantage of I2C, so as a conclusion, advantage of I2C, good for communication with onboard devices that are accessed occasionally, okay, or the data rate is not that high, like temperature. You don't need to read many times per second. Easy to link multiple devices because of the addressing scheme, and also because of the use of open collector and so on. And then it's quite cheap. A disadvantage is complexity of supporting software components can be higher than competing schemes. Okay, so this one can be more complex than if you use SPI. Okay, because we need to talk about SPI because SPI is also quite popular. Okay, so let's take a 10-minute break, and after that, the SPI we have analog, and then that's it for today lah. Okay, so 10-minute break starting from now. Right, welcome back. Okay, so now we going to discuss about SPI. Okay. One back yet? I hope so. Okay. So SPI. SPI is a synchronous standard by Motorola or at the same time as I2C. Like I2C, it's low complexity, low cost. Also intended for operation on a single board. Also used for EEPROM, flash, and real-time clocks. Okay, so we like I2C, but unlike I2C, it's generally faster, can be clocked up to 50 megahertz, and better for point-to-point data transfer and data stream, or high-speed data where the data come in blocks. Okay, for example, ADC converter or SD cards. One of the applications of SPI until today is on the micro SD card. So the micro SD card use the same, well, it uses exactly, it uses the SPI standard. So the standard has 4 wires. One is the clock, serial clock. Okay, if you compare this with I2C, we have the same idea, serial clock. But for data, there's 2 wires. Okay, so in I2C, only 1 wire for data coming and going. For SPI, there's separate wires for data going from master and data coming into master. So the first one is called MOSI, master out slave in. The other one is master in slave out, or also sometimes called SDO and SDI. And then lastly, there's a third pin, fourth, okay, called the slave select. This is input to enable the slave, okay, to select which slave communicate with the master. If you have only one slave, you can even skip the configuration of this pin. Okay, so for one master, one slave communication, you can see here we don't have to include the slave select pin. So the master and slave are connected in a form of circular buffer. So there are a shift register, but the shift register is connected. So the shift register becomes like a big shift register with a size of 16 bits. And connection is always full duplex. That means data comes and goes at the same time. And depending on what you're doing, the data may not be meaningful. So if you are transmitting, so data going from master to the slave, or data going out is going to have useful data, but data coming back from the slave will not be meaningful. Similarly, if you are reading data, then you only read the data coming in and not the data coming out. So there will be some data there because the data comes from a register, but the data may not have any meaning, so be garbage. So you have to know what you're doing. So for point-to-point, SPI is simple and efficient because there's no addressing needed. So less overhead. So if you want to send one piece of data, just send, you only need 8 clock cycles. So the data will be transmitted. You don't need to send the address, and you don't need to wait for acknowledge and so on. So less overhead. And also because it's duplex, so theoretically you can send data and receive data at the same time if you want. But if you have multiple slaves, like this example later, okay, maybe you have 3 slaves at the same time or at the same board, then slightly more complex because you must have a separate slave select signal. So you have to choose which slave you want to communicate, and you talk to the device only. Okay. Okay, and then when you want to transfer data, you have to know the phase of the clock and the polarity. So there's a total of combination of four polarity and phase combinations. There's a total of 4 polarity and phase combinations. So if you look at this column or this table, we have C pol and C clock polarity column and clock phase column. And the combination determines which clock edge is used for data transfer. So clock polarity 0 means active state is 0. Clock polarity 1 means look here. Clock if CPOL is 0, the ideal state is 0, active state is 1. If CPOL is 1, then the ideal state is 1, active state is 0. Then the clock phase is when is the data transfer being done. So you have to know which one is idle, which one is active lah. So 0 means data is transferred during idle to active. So if it's 0, 0, that means idle state is 0, active state is 1. So idle to active means 0 to 1, going from 0 to 1. So the data, the clock edge for data transfer will be low to high or 0 to 1. So there's a total of 4, and then you can see on the right here, there's low to high, high to low, and low to high. So that's the basic. And because of the combination of 4 things, the data transfer can happen either during clock going up or clock going down. So if you look at the group of signals in the middle here, compared to the group at the bottom, the data is offset by half a clock cycle. So that's the difference. That's what the combination of CPOL and CPHA will do. Okay, so if you have more than one slave, you can connect 2 ways, either independent slave or daisy chain slave. If you use independent slave, that means each slave will have a separate slave select. So here we have 1 master, 3 slave. So we will need 3 slave select pins from the master. If we use daisy chain slave, what happens is you have the same slave select to all the devices, but you can see that the MOSI output from the master goes to MOSI from the first slave, but the MISO pin from the slave number 1 goes to MOSI of number 2. It doesn't go back to the master like in the first arrangement. So by using daisy chain, you will save the pin on the master. So the master now only have to keep 1 slave select pin, but data will take longer to arrive. So let's say I have data from the green slave. I want to read data from the green slave. So the data will go to the blue slave and the purple slave before it goes to the master. So it takes longer. So basically you have a longer shift register. So that's what happens. So it's your choice. You want, if you have many pins, you should select independent slave. Okay, so advantage of SPI. Okay, basically they are both slow and cheap, and I2C can you can put more devices on a single bus, but for SPI it's faster. Okay, so slow slow here is in relative lah. Okay, so SPI is relatively slow compared to like other devices, but still faster than I2C. So SPI is easy to use for streaming, and then there's no addressing. But the problem with SPI is you need to have a separate slave select. So that can be a problem in certain situations. And then there's no acknowledgement. So cannot tell if the clocking is sending you garbage. Then there's no arbitration. So if you have two or more devices trying to send data at the same time, it's harder to implement. Then there's no flow control. So there's no acknowledge. So if the receiver is slow, you will get garbage. So before you connect the component to the master, you must know the capability of the device first. Okay, so that is a very short section. Then we go to analog lah. So this is the last for today. So for analog, we have quite a long discussion. So first we go to the overview of analog to digital converter. So the analog to digital converter or ADC convert the analog voltage to a value that you can use. So any analog value you can probably convert and read, but you must convert to a voltage. Okay, so even current you have to convert to voltage before the ADC can convert that to digital. And the output of the ADC is represented by this formula. We have Vin divided by Vref. We have the unknown voltage plus the reference voltage, or divided by the reference voltage, and then multiply that by the 2 to the power of output bits. So the output bits is typically 6 to 12. Can be more, not normally at least 6 lah. Okay, if less than 6, it's not really useful. So the smallest detectable change on the ADC is the resolution. Okay, so it depends on the width of the digital output word. So if you have, for example, 10-bit ADC, you will have 2 power 10, 2 to the power 10 or 1024 steps. So if you have 10 bits, that means you can resolve 1 out of 1024 different voltages. If you have only 8 bits, then you have 256 different voltages that the system can differentiate. So higher resolution is more accurate lah. So it will represent the input voltage more accurately. And then we have the sampling rate, Fs, okay? F of S. So the sampling rate must be at least twice the highest frequency of the signal. For example, on the CD, normally we have the for the CD it's fixed lah, it's 44.1, but now internet audio we can have other values as well. But if you have a whole compact disc, it uses 44.1 because the human ear can listen up to 20 kilohertz. Some people can hear above lah, but 99% of people can go up to 20. So that means your sampling rate has to be slightly higher than twice, 40, okay? 40 or something. So 44 is the one chosen by Sony when they first come up with compact disc. And then we have the speed or the maximum output rate expressed as samples per second. Okay, it's related to sampling rate. So speed of your ADC, if you want to sample CD quality audio, must be able to go at least 44.1 kilo samples. Then we have accuracy, which is the degree of conformity of the digital code representing the analog voltage. So all this, okay, the resolution, the sampling rate, and the speed, altogether, they contribute to the accuracy. So higher sampling rate and higher resolution will be more accurate or less error compared to the original analog voltage. So in practical use, we have 4 different types of ADC. First one is dual slope, and then we have flash ADC, successive approximation and sigma delta. So in this graph, we try to simplify the differences in terms of speed and the resolution and the cost. Okay, so flash ADC has lower resolution. Okay, it can go to 4, maybe 12. That's the maximum. That's the best. The flash is very fast, but it's very hard, very costly, very expensive, very fast and very expensive. And it can go only to maybe 12 bits. Higher than that, it's very expensive. But for some applications, people have to use flash, for example, in video. So for video, you have to sample many pixels per second. Then flash is the only way to do it. For other applications that you don't need high speed, you can try other methods. So you can go dual slope, successive approximation, or sigma delta. So sigma delta is the approach where you try to go very cheap, okay, but it's also very slow. So somewhere in the middle is the successive approximation, which is used in most microcontrollers, including STM32. So for the successive approximation register, the conversion must be done in a few clock cycles. So let's say your ADC has 8 bits resolution. So you will need 8 clock cycles, convert from digital to analog. Each clock cycle, you will converge to the exact value. So for example, here, first clock cycle, okay, you will fix the MSB first. Okay. So here you can see, first clock cycle, you will compare your voltage with you will check the voltage, whether you will, this is your unknown voltage, it is V unknown, and then you compare with half the V over 2. Okay. So if your voltage is higher than V over 2, you will know that the first bit is 1. So bit number 1 is set, because your voltage is higher than number 2. Then you will compare, you will compare your unknown voltage with 3 times 3 over 4. Here lah. So this is your unknown voltage, the blue one. Then here is the red one. The red one is the comparator value, which is generated by the D2A converter. Okay. So the second clock cycle, the D2A will output B times 3 divided by 4. Compare again. Now you can see that the voltage is still higher than this. So second clock cycle, you will fix the second bit. Third clock cycle, I think here in this example, it will try P7 by 8. It will compare with basically the V unknown. It will compare with 1 1 1 0 0 0. Okay. So the logic here will put 1 1 1 0 0 0 0. Okay. So that will give you V7. Okay. Compare again. In this case, it happened that the voltage that you have is lower. So that you know that the third bit is 0. So on lah. So it will take a few clock cycles. So if it's an 8-bit system, it will take at least 8 clock cycles, plus overhead to load the register and so on, maybe 10 clock cycles.
Oh, so
yeah,
cannot understand.
Can understand. So I have to repeat again. Okay, it's like this. The blue line is your voltage, your unknown voltage. Okay. So first clock cycle, what happened is the SAR logic, the controller will test your voltage, your unknown voltage with 1 0 0 0 0. Will test only. So that is actually this value 1000 divided by 111111 is actually V by divided by 2. Okay. So if you convert that, it will be like this. The voltage that is being outputted from the DAC is V by 2. Divided by 2. Okay, you want okay, yeah? So
why we need to divide by the 1111111?
Because you want to that's the way it works. You test from the MSB first. Okay, you want to check the MSB. Right now we want to convert this unknown value to a certain value here lah. Finally, after the conversion is finished. But to do that, you have to convert using binary search. This is binary search. Okay, you have a lot of voltage. Okay, you have 0 to 255. Now you want to narrow. This is your unknown voltage. Your unknown voltage is here. So you have to know. First, you have to divide by half. Okay, this is V by 2. Okay. In which block is your unknown voltage? Is it this side or this side? Is it lower than V by reference voltage by 2, or I should put Vref. Okay, sorry. Yeah. So is it lower than Vref by 2 or higher than Vref by 2? So the controller logic will output Vref by 2 and you compare. So this is a comparator. Because your voltage is here, right? The blue one. Your voltage is blue, and Vref by 2 is the red one. So here we'll give 1. That means your V unknown is greater than Vref divided by 2. Okay, first clock cycle. Okay, what does it do? What does this step do? It just fix. Just say, okay, this is correct. That's all. It only knows that so far we know that the first bit is 1. But the rest we do not know yet. We need more clock cycles to check the other bits. Okay, need to repeat. If your voltage is on below Vref by 2, you will be 0 and dash dash dash. You don't know yet lah. If your voltage is higher than Vref divided by 2, you would know your voltage will be 1 and then something like that. So first clock cycle we just want to know what is the first bit. So if your voltage is higher than Vref by 2, your first bit will be 1. So you need 1 clock cycle just to check that. Can or not? Quiet. Okay, good.
Then after that lah.
After that, okay. After that, then you zoom in again. So now you know the voltage is between Vref by 2 to Vref, right? But in this case, I want to know the second bit. So I know the first bit is 1, but the second bit I do not know yet. And then I have other bits to finish later lah. So now we want to know the second bit. The second bit here is going to be between Vref by 2 or Vref. So I will split this again. So this one is actually Vref 3 by 4 lah, right? Midway between Vref by 2 to Vref is Vref 3 by 4, correct? So I want to know whether this side or this side. Because the answer here can be 1, 0, dash, 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 or 1, 1, dash, dash, dash. I want to know what the second bit. So the way to do it is, I will, the controller logic will send 1, 1, 0, 0, 0. So which is Vref by 4. Okay. So your unknown value is compared against Vref times 3 by 4, or 3/4. Yeah, here, this one, red one. Okay, it's EREF 3/4. You see this? This is EREF. This is EREF by half. This is EREF 3/4. So second clock cycle, we compare against 3/4. And the voltage, the blue line is still higher. So I still get one here. So now what I do is, second clock cycle, I decided that second bit is. So I only know now information I have is I have the value will be, the final value will be 1, 1, and then I don't know yet. Later we'll find out. Okay. So what to do next? The system will output 1, 1, 1, 0, 0, 0. Yes. Okay. 1, 1, 1, 0, 0, 0, which is this green value here. Okay, that is the test value. And for the third clock cycle, the V unknown is actually less. So I have 0 here. Okay, so the green one is output from the ADC. If you give 1, 1, 1, 0, 0, 0, 0, 0. But here we see that the blue line is less. So I get 0 here. This 0 gets stored in the result. So for the third bit, I will get 0 here. See this? It's green. When it's green, that means the comparator detect that the value is less. So that value will be locked. Okay, so we finish with 3 bits. So the next one, I will test against 1, 1, 0. The 3 bit already confirmed, but for the 4th bit, the tester or the controller will give 1, 1, 0, 1, 0, 0. Compare again. So 4th clock cycle, red, green, red, green lah. So here we can see here, red, red, green, red, green, red, red. So on. So lastly, we get all 8 bits. Okay, so red twice, and then green, red, green.
What is the color indicating, sir?
The color indicating that okay, I delete this. The color indicate that the test voltage is less or greater than the value that you do not know, that you inputting. Okay, so if red here, that means red, it means the voltage unknown is greater than the test voltage. So this is like a test voltage. It will check. Okay, it will test, and then it's like you're trying to. Okay, I give you a number. Have you played this game? Okay, get a give me a number between 1 to 10. Okay, 1 to 10. Don't tell me what number. Okay, and then I will try to guess what is the number. So of course, I will test 5 first, right? You say, okay, if your number is 7, you can tell me, okay, the number is greater than 5. So now you know that the number is between 5 and 10. I don't have to check 1 to 4. Same thing here. Slowly afterward, after 3 or 4, maximum 3 question, you already know the answer. The same thing here lah. If you have 256 different logic values, you divide by half every time. Then in 8 clock cycle, you will get the answer. So the color red here means that whatever you are checking, whatever you are testing, is less than the unknown voltage. If green, that means the green means the V unknown, U and K is less than V test. But the testing value is generated by the control logic. Test. Maybe too many bits. So that's why it takes a long time to explain.
Hi, doctor.
Yeah.
Is the value, I mean, inside the bracket is the result of comparator? Am I right?
Check the bracket.
Yep, I mean the
course, these
color
are-
one. The bracket inside the bracket, is it the output
yeah.
of the comparator?
Yeah. You put the comparator here, and
Oh,
then
okay.
and then it will store directly as the result lah. So now it will lock that. Okay, slowly it will lock. So first you do not know. Okay, so first you do not know, and then after the first comparison, you confirm that the first bit is 1. So the moment you is red or green, you lock the value lah. So basically here, as you move along, this value more and more bits get confirmed.
Okay, got it. Thanks.
Maybe you should try find binary search algorithm. This is basically binary search lah. You can find, for example, binary search in Wikipedia, and then maybe some animation. Same idea lah. Okay, it's something that you do not know. You have to split it to half first, and then you eliminate the other half. Slowly converge to the result. Okay, so I think if you want to discuss further, you can ask me later. You can find maybe other tutorials later. Not clear, you can try to find some animation or some sort. Okay, so anyway, this is the method lah. So most microcontroller will use this method because it's quite cheap. Okay, the D2A is quite cheap. You only need a D2A, control logic, and comparator. And also we have also something called the SNH, the sample and hold. The function is so that you will lock the value. This is like a capacitor. There's only a capacitor here lah. When you sample the data, you have to turn off the input to the outside world. Otherwise, the value may change while you are doing the calculation. So you have to sample the value from the V-in and hold it. At that time, you cut off from the outside. Because the value, if you're sampling real data, the value from outside may be changing. So you don't want the value that you are trying to compare changing while you are still trying to convert. So you have a sample and hold circuit there. Okay, so on the STM, we have 12-bit SAR ADC, and it's programmable. So if you want higher precision, you can go to 12, but as you see, the more number of bits, the slower it will take to convert. So you have to balance whether you want speed or accuracy. Then the conversion time is number of bits plus 3 clock cycles. Okay, so of course you have to load register here and whatever, store the result and so on. So it's a constant 3 clock cycles. And then the supply requirement is 2.4 to 3.6. Okay, this is separate than the supply voltage for the processor. Normally, on the processor we have the VDD or the VSS, right? But for an analog, there's always there's a pin there called VREF. So this can be different, slightly different. Not too different, but slightly different, can be slightly different than the supply voltage. So if your analog value can go up to 2.5, then okay lah, just use 2.5, then you don't have to convert anything. Right, and then from the whole system here, we have 16 channel from outside and 3 internal channel. Okay, so that means you can sample up to 16 different values from outside. And then there's also 3 internal channels from the processor itself. And on the ARM is quite complex. You can have serial conversion, continuous conversion, scan, discontinuous. So we just we will just show an example for single. The others are quite complex. The computation is really, really complicated to understand also. And then you can also do conversion by groups. So you can, for example, scan your read 8 inputs in one shot. So then you have a regular group. But in the middle there, you can have injected group, basically like interrupt. You have nested interrupt. While you are reading data, you can have another set of higher priority data you can inject. So quite complex lah. So we don't discuss that. Then we can have DMA, we can have interrupt, and then there's also a watchdog. Okay, so if your input voltage goes outside the threshold, also it can cause an interrupt. So to use it, because it's complex, so to use it is also quite complicated lah. So that's why we normally don't handle it manually lah. So it's a lot of registers to set, and you have to know everything about the register before you can manage. So it's better just to use HAL, but even to use HAL, you have to know what to set. So HAL, you have to watch out the handle. Okay. So the minimum thing you have to know is listed here. Then you also have the unit type def. Okay, so these are the settings for each conversion. For example, here we have this page. Okay, there's many things here. So for this page, I listed 5 and then continue some more. Okay, so for example, here we can set the clock prescaler. So on the STM32, there's many clock sources. So to control the clocking for the ADC, you choose the relationship between the clock and the speed of your conversion that you want. So you can divide by 2, by 4, by 6, by 8. Then we can select the resolution. This is expected. And then we can have selection of data alignment, whether it's left justified or right justified. So for example, if your data is 10 bits, this is a 16-bit, right? So you can have left justified. So your 10 bits is here, unknown here. Or you can have right justified. You can have 10-bit data here, and then the unknown on the left. So you can even select that. Then we can choose whether you are doing scan mode. Scanning means you do multi-channel at once or single. Then we can select whether the end of conversion flag is set at the end of each conversion in the scan or after you finish scanning the whole set. AOC is the end of conversion flag. I forgot here lah. So after you finish here, you have AOC. So if we are using the ADC, this one will be internal. We do not know. We just wait for the AOC one, then we can read the data. And at that time, the data here is ready. Don't try to read the data before AOC is one. Okay. Then we have the other setting is more on the how to use the continuous mode lah. So you have continuous conversion, and then you can set DMA for continuous request. And then you can set the number of conversions when you do by group. And set whether it's discontinuous. Okay, discontinuous means let's say you have 8 channels you want to read, you can stop in the middle and then continue later. And then here, how something to do with the discontinuous conversion. And then second last here is the external trigger. How do you want to trigger the conversion? Do you want it to be based on the external event, or is it going to be from the software? Then the external event is a clock edge. So the clock edge can be rising edge, falling edge, or any edge. If you are doing by software, then you select this to be none. So that will be software initiated trigger. So the external trigger conversion edge is meaningless. So like this lah. So you have single, okay, you start the conversion, which channel, stop. Or you can have single continuous. So it will keep on converting continuously. It will never stop. Or you can have multi-channel, okay, channel 1 through channel 7, for example. After that, you stop. So scan multi-channel, or you can have scale continuous. Okay, you do your read channel 0 to channel 7. After you finish channel 7, go back to channel 1 and keep on doing that continuously. And lastly, you have discontinuous. You can have almost like continuous, but you can stop and start. So after you scan a bit, you stop it and then start it again. So many modes. I will just stick with the first one lah. It's the easiest. Okay, so the easiest way is just to use the single conversion and pole mode. So to do that, you still need to know many things. You have to enable the clock. You have to enable the GPIO pin that you want to use. Configure the GPIO pin as analog. Configure the speed. Enable continuous measurement. Okay. Then you use the STM cube. So just focus on the application. Okay, yeah. If you use continuous, then you just read lah. You just read the data. You don't. Whenever you want, you can read the data without having to start again. Okay. So here is example of how you can experiment. You can put potentiometer and then hook it to pin A0 here. This is your analog input. The red wire is the 3.3 for the reference voltage, and then we have ground. Basically you are trying to read pin A0. Okay, so go through STM here, select pin A0. So on last, actually the step here, there's more steps than I have here. You have to do all the settings here. Settings there. Okay. And let's say you don't have any problem with that. Okay, so this is the code. Okay, as usual, this one is generated from STM-Cube. Many comments, deleted all. Okay, only take the important part. So we have to include here on top, and then we have the handle. And then this one, what we want to do is just like the temperature just now. We convert the voltage to string, and then we send it to UART. So we will need to use the UART also. So we have the handle ADC and the handle UART, two handles there. And then if you look at the code, this one is quite standard. Okay, HAL init, clock config, initialize the GPIO, and then initialize the port that you want. So you see UART here and ADC here, as expected, because we want to use both peripherals. And then this is the main loop lah. So while one, start the conversion, and then we wait for the AOC. But we don't really look for the AOC pin or the AOC bit. It's in there because we are using HAL. You don't need to go to the pin and check which register. Just call HAL ADC pole for conversion and assign the max delay. Okay, and then the value will be dumped into the handle. So this is a blocking. It's a blocking function. So if there's no problem, we will get here. Okay. Go to the next line, and then the next line, we extract the value from the handle. So the handle is, we see the handle, right? It's quite complex, but inside the handle, there's a value there. So to extract the value from the handle, you use the ADC get value. So you don't go directly to the register, but you use HAL function to fill in the handle structure. You read it from the handle structure. So you get this value, convert that to unsigned, okay, hexadecimal, and then transmit to UART. And then we have some delay here just to, you must have a delay. Normally for any of this IO, you must have a delay. One doesn't work, maybe put 1000 or something. Okay. more like a trial and error. You don't force the I/O devices to work immediately. Okay, sometimes it's not capable of doing that, so just add some delay there. Okay, so there's also other functions lah. So this is the main function. In Cube, normally there's other function at the bottom, so that's why we have these prototypes. So you will see also this function, this function, this function in the code. Ignore those. They will be there. Just don't touch anything. Just compile. Okay. So if you decided to try that project, build it, and then run the code on the open the terminal, and you should see the values in hexadecimal because here I use hexadecimal. Not hexadecimal, H. Actually, I'm not sure. Change to whatever lah. This one, U is unsigned, but H, forgot actually. What is the format there? So because we are using 10 bits, so that means 0 is 0 volts and 4095 is 3.3 volts. Okay, why? It's because we are using 10 bits resolutions. So 2 power 10 will become 1000. Okay, this is 12 bits now. Okay, 2 power 12. Yeah, 2 power 12 will become 4096. 2 to the power 10 is only 1023. So 2 power 12 minus 1 is 24095. So but 2 power 12 is 4096. So the range of values will be 0 to 4095. And 4095 will represent the highest voltage of 3.3 volts or whatever the value of the VREF. Okay, so if you just want to experiment and don't want to use a different VREF, just use 3.3. And if you want to see changes in the values printed on the monitor, just try to turn this potentiometer will change the resistor value and get a different analog voltage. Okay, so if you want to do interrupt, have to do more work lah, but this one we're going to go in detail. So you can see here for interrupt some changes. So you can, if you recall this code here, this is just the main loop. But if you are doing to do interrupt, you can see that you start the interrupt, then you take the data from somewhere, and you transfer. You can do whatever you like with the data, but you must provide a callback function, and in the callback function will get the data from the handle. You must provide the callback function to read the data. Because this is HAL, you don't actually read the register. You read the data from structure. Okay. And then if you do DMA, of course you need to set up the DMA. And in this case, DMA is very fast, so not suitable to use for UART. For UART, maybe the UART itself is the bottleneck. So very fast data coming from DMA and try to send data to slow UART is not suitable. So what this example is doing is to convert the value from the ADC. Okay, so this is your ADC. This is your V unknown, okay, from your potentiometer. Go to the processor and then go to PWM. So PWM, we don't have the notes for this semester. Maybe next semester I will try to prepare the notes. What PWM is called is a pulse width modulation. Okay, so normally people use this on laptop to control your LCD screen. And poorly designed laptops like a Lenovo, the old Lenovo ThinkPad, you can see flickering. So if you want dim LED, dim display on your LCD display, you will turn on the LCD for a very short time. Okay, so on your eyes will average out. So you will look at it and you can see that the monitor is dim. If you turn on the brightness, it will be like this. Okay, so longer time high and the short time low. So this is the idea of PWM. And PWM is built into most chips lah. Okay. So it's a matter of using, but we are behind that in the regard lah. So remember the chip just now. Let's see, do we know? Okay, see this? This one also have PWM actually, okay, but somehow not listed. So PWM can be sort of a digital to analog lah. Okay. So what this example is doing is read data from outside, convert to PWM. So higher voltage here will be longer time on and shorter off. If you put it value low, then a longer time off, shorter time high. So if you connect this to LED, the LED will be dim. So this is dim and this is bright LED. If you connect to LED. So you need to use a timer, and the timer have to be programmed and so on. So this one, unfortunately, we don't study this semester. If you want, you can do it yourself. Okay, so to finish up the chapter, you can see that there's many other ways to use it. Instead of the single channel, you can use multi-channel. And if you use multi-channel, you have to be aware of what's called the rank. I think this one, the first one is more familiar. It will take over after this, from 4 to 5. So this one, are you ready? And then, as we know, there's the online manual, which is quite thick. So just click here.
Hello, hello. You are calling for me?
Yeah.
You got heavy rain here. Just 1 second.
You take over after this.
It's
up to you lah. You want to continue tomorrow also can. I'm almost done.
Hello, can you hear me now?
Yeah, sure, clear.
Okay, yeah, okay, all right. So then I think it's already 4 p.m. So we'll just continue tomorrow morning.
Okay.
All right. Okay, so tomorrow we'll have a quiz from 9 to 9:30. All right. Then after that, maybe 9:45 we can start our class. Okay. All right. So I guess yeah.
Do you mind to have more briefing on the tomorrow presentations, like, or that's all the information that we have from the WhatsApp message?
Yeah, Dr. Osman, you better give a briefing now, or even for me. It's useful for me also.
I can't hear you, Piamoni. What do you say?
Give a briefing on what's expected on the tomorrow demo.
Okay, so I guess maybe we can look at this what we call assessment sheet. Okay. So basically that would be let me just double check. So milestone 1, 2, 3, 4. So I think you have done your video already or not? Then work procedures later, conference papers later. So it will be just based on your video lah. Okay, so because your video is due. Let me just double check. Just 1 second. I'm scrolling through the class assessment sheet. So, so on the 12th and 13th, that is today and tomorrow, that we have a 7-minute per group Q&A, and that you also are supposed to complete milestone 4, and milestone 4 is actually your final product video. All right. So based on the video, you just play back your video to us. And based on that, we're just going to ask some questions. So let's look at what's the contents of milestone number 4. It's talking about your video, your participation, your organization, media, content, algorithm. So and then we'll be looking at what are the things you have done, and if you have any queries on what kind of algorithm you have implemented, and the hardware interfacing, and the STM32 strengths that you exploit. So those are the technical content that we can ask lah. All right. So since that's milestone number 4, Milestone number 5 and 6 is actually your report. Let me scroll back. Milestone number 5 is work procedure documentation, and milestone number 6 is a paper. That's basically your final report lah. Okay, so those things are due on the 20th. That is another week or so from now. 7-8 days from now lah. Okay, so there are no questions on that. So that one is you just submit your GitHub thing and also your paper. All right. So that will be next week. So for tomorrow, it will just be your video and anything that based on the video lah. What kind of things that you have achieved.
Yeah. So okay, for tomorrow maybe we'll add more things lah for the
All right.
stuff.
Did I answer your question?
Yes, definitely. Thank you, sir.
So I will just we will be evaluating you based on the rubric given. So it's pretty objective. So we won't deviate much from that, but we may be asking some questions that's out of the rubric just for understanding what you're doing, and also for us to learn more. Also, yeah, but the primary questions that actually contribute to the marks will be basically directly from the rubrics. All right, thank you. So any more questions?